So I'm Gautier Izacard. I'm a PhD student at École Normale Supérieure, and I'm working at Meta AI. I will, in this talk, I will present and discuss some work on retrieval-augmented language models. So to start on the trend started by Sergey, I have few questions for the room. Who has already heard of large language models? Raise your hands. Okay, so this will be quite fast. Who has heard of GPT-3? Okay, prompting, I guess. Relatively, okay. Great. So I can probably skip the slide. Okay, so joke aside, there are large language models everywhere, and most of them are transformers. And so I think the most remarkable instantiation of them are GPT-3, Chinchilla, and Palm, which are extremely large models that have been trained on a gigantic amount of data, like 1.5 trillion tokens for Chinchilla. And a key characteristic of them is that they exhibit some form of generalization reflected by their ability to generalize from few examples. So if you want to solve a new task via prompting, so if you want to solve a new task, just give an example or two to the model, and then ask him your real, the real example that you would like to solve, and the expectation is that the model will generate something that makes sense. So, I mean, it's an expectation, doesn't always work. And so, there is an echo. No, it's okay. And so a key feature of this few-shot performance is that it increases a lot with model size. And so on the right, it's a plot from a paper by Jason Wei. And so the goal of this paper is to show that at a certain size, this model will exhibit a sudden jump in performance. So the dashed line is random performance, and you can see that starting from a certain size, there will be a sharp increase in performance. So all the tasks here are cherry-picked. And but on the left, I've chosen another task that is commonly used to benchmark large language models, that is natural questions. And most of the tasks that are used to benchmark large language models will require these models to store knowledge and access information that is contained in their parameters. So for instance, there is MMLU, which is a set of real-world examinations designed for humans, framed as a multi-choice question answering task. So here is an example. When an influenza virus enters a cell, it immediately starts to do which of the following, and then model is expected to select the correct answer. Question answering, for instance, what element did Marie Curie name after a native land, polonium, or fact-checking. And an alternative to large language model is a retrieval-augmented language model, where the basic idea is to augment a language model with an external memory. So in this memory, we can put Wikipedia, some part of the web, or GitHub, for instance. All this model built on the fact that retrieval and search is generally efficient at scale. And these models are not new. They already achieve state-of-the-art performance on knowledge-intensive tasks like question answering, fact-checking, or dialogue. And I think that the opposition that there is between large language models that store information in their weights and having an explicit memory raises several fundamental questions. One of them is how to memorize. And adjacent to it is the role of memorization in large language models. What is due to the data? What is due to some generalization aspects? And another question that I'm quite excited about is that retrieval-augmented language models decouple memorization from reasoning in some ways. And this is relatively similar to the way we perform some tasks, like coding, where we spend a lot of time on Stack Overflow and we use existing snippets of code. I mean, I am at least, maybe not the rest of the room, but that's the way I'm coding in general. And so the similarity between the way retrieval-augmented language models works and the way we work, I think there is good reason to believe that this is potentially a useful prior. I've no clear evidence for this, but maybe. And so a very standard retrieval-augmented architecture is retrieve and read architecture, where the model is composed of two modules: a retriever that, given a query, selects a relevant document from a corpus, and a reader which performs generation condition on the query and retrieve documents. So here below is an example with a question answering example. So for the question, what element did Marie Curie name after a native land? The retriever has access to Wikipedia as a knowledge source. It retrieved documents that may or may not be relevant. And then the reader task is to generate polonium, which is the answer. So again, this architecture have been out there for quite a long time. So here is a partial list of what exists in the literature. So it started with Dr. Query, Realm, RAG, Feed, and more recently some work by DeepMind called Retro, which exhibits strong language modeling performance. Now I will start to present our very recent work, Atlas, where we explore the few-shot abilities of this retrieval-augmented language model. It's a work with a lot of colleagues from Meta AI. So right now, until very recently, retrieval-augmented language models were constrained to tasks where they were trained on a relatively large training set with a bit more than 10K training sample generally, and there were no few-shot results. So our aim in this paper is to provide some initial few-shot results. Yeah. No? Okay, great. So a key ingredient to obtain good few-shot performance is to pre-train this kind of retrieval-augmented language model as a retrieval-augmented language model. So this is the task depicted at the top of the figure. So we use a mass language modeling task where we put a mask in the input and ask the model to fill the gap. We also tried with a language modeling task. They work relatively similarly. And I think one of the reasons why people didn't really use them, do this before, is that it has a very limited impact when the dataset size is sufficiently large. So it's really important for few-shot performance, but to adapt the model to use documents. But it's still relatively fast when your dataset is large enough. Okay, and so this model built a lot on our previous work that I will now detail. But to give you some initial aspect, the reader and the retriever are trained jointly. That means that the parameters are updated simultaneously during training. For the reader, it's relatively obvious how to train it. Like it's a basic language model that is conditioned on retrieved documents. But for the retriever, it's less trivial, and for this, we distill signal from the reader to train the retriever. The reader architecture is a fusion decoder architecture initialized with T5 model from Google, and we use a model that is the largest model that we use contains 11 billion parameters, and the retriever is initialized with Contriever. For the retrieval corpus, we use 400 million documents from the web and from Wikipedia. Okay, so the first piece of the model, the first part of the model is to be able to retrieve relevant documents given an input, a piece of text as input. That can be any kind of text, really. That's the goal. And so traditionally, for this, people have used lexical-based approaches like BM25 or TF-IDF. These methods compute exact matches between terms of the query and terms of the documents, and weighting the terms based on their importance. They discard the most common words. And more recently, dense retrievers have appeared as an alternative by encoder architecture, where query and document are encoded independently from each other, and then the similarity score between a query and a document is obtained by doing a dot product between query and document representations. An advantage of these neural-based retrievers is that they can be trained and adapted to specific tasks, and they work well with sufficient training data. So in our model, the retriever is initialized with Contriever, which is a model that we pre-trained in a previous work. It's an unsupervised dense retriever pre-trained with contrastive learning, where we basically take piece of text, do 2 random crops, and ask the model to pair them among a pool of negatives that are also other pair of random text. There are several benefits to this pre-training. One of them is that it improved performance after fine-tuning. It's also improved robustness when there is domain change or domain or task changes. It has also good unsupervised performance. It's on par with BM25 on question answering tasks. From an historical perspective, until 2019, supervised dense retrievers were outperformed by BM25, so the neural search revolution is relatively recent. So now we have initialized the retriever. It's an unsupervised retriever. It's decent, but not great at any task. How do we further train it to make it really good? So annotation for information retrieval are generally expensive because for all queries in the corpus, you would like annotation for all documents in the corpus. So when the corpus is contains several million documents, this is not possible. Incomplete. In general, there is only one positive document for each query, while there might be other positive documents in the corpus. And biased because in order to make annotation possible, an existing retrieval system is used to pre-select documents. And so to work around this issue, we distill signal acquired by the reader on input-output pairs to train the retriever. So how does this work? So for question answering, for instance, instead of using pairs of question document containing the answer, we use only question-answer pairs. So for this, you can use attention scores. And the idea is that the more a document is attended in the transformer, the more relevant it is. And then other people have used perplexity, like you just look at the perplexity of a generation condition on the query and the document. The lower the perplexity, the better the document. And so all this works well, but it requires non-random document to start. Otherwise, the model performing generation just learns to ignore documents, and you don't have any positive feedback signal. And so for this, we have a decent enough unsupervised retriever, so all this is fine. Now, the last part of the pipeline is that we have a query, we retrieve documents, now we want to generate. So now, for this, we use a fusion encoder architecture. It's now a relatively old work. Before this work, architecture for this kind of problems have either one of the two issues. Either they had a quadratic attention, like the scaling was quadratic with the number of documents, or performance saturated very quickly, around 10 to 20 documents. So fusion encoder is a simple modification of a sequence-to-sequence model. It encodes each document with a query independently from other documents, and then representation are merged in the decoder. So this allows for linear scaling with the number of documents and performance improvement up to 100 passages. So now the result, sorry. On question answering, we obtain generally great results, both for few-shot learning and for fine-tuning on the full data sets. Notably for few-shot learning, with 64 examples, our model is better than Palm, which has up to 50 times more parameters. So this is a table on MMLU, which is the dataset composed of real-world exams. So the most standard way to evaluate on this benchmark is the 5-shot result in the middle. So performance is in between GPT-3 and recent model from DeepMind like Gautier and Chinchilla. And there are two interesting things I think in this table. The first one is that a 0-shot performance is on par with the 5-shot performance. And the other thing is that this dataset is used in the emergence picture that I showed you at the beginning, where basically the performance jumped at some number of parameters. So until now, this number of parameters where performance starts from random to good was 70 billion. Here the model is contains 11 billion parameters, and training cost is way cheaper than other models. And so this kind of means that the memorization aspect is a bottleneck for this kind of task for large language models, and that the emergence of this property that models start to become decent on this task is mainly an issue of memorization here, because with a smaller model, we also have non-random performance with our retrieval-augmented pipeline. So I will skip this slide. No. Oh, yeah, okay. So another advantage of retrieval-augmented language model is that they can be updated. So retrieval is performed on a corpus, and this corpus, once, for instance, the president of the United States changes, can be changed to reflect this change of information. So on top is a dataset where answers differs from 2017 to 2020. And so if we train on 2017 answers, have Wikipedia 2017 and test on 2017 answers, we obtain 77% of accuracy. If we test on 2020 answers in the same setting, performance drop to 1.5. So this is on the top. Yeah, it's here. If we switch the index to the 2020 index, it jump up to 53, which is very close to 60, which is obtained if we train on 2020 answers. So this is one of the advantages of retrieval-augmented language model, the fact that the database or the knowledge source, or however you want to call it, can be updated. And that's it for Atlas. But what is next for retrieval-augmented language models? I believe a lot of promise and challenges. So a big caveat to the few-shot results I've presented, it's aside of the zero-shot results on MMLU, is that they've been obtained with fine-tuning, not with in-context prompting or few-shot like other large language models. Mainly because we didn't have a good a model able to perform well on in-context few-shot. Another issue that is hampering development of this kind of model is that they are more complex than large language models. Like for large language models, people have been able to dedicate a lot of energy to scaling because they are conceptually very simple. And also, I've mentioned several times that our model is way smaller than large language models. So this is true, but processing retrieved document has a cost. And so if we take a look at the computation cost, it's not exactly the same picture. So an area where I would love to see improvements being done is, can we improve documents by preprocessing them, either converting them into some continuous representation or improving their discrete representation. So these are a lot of changes, but I think there are also hope and promise that this is an interesting direction. So first of all, there are strong performance on a variety of NLP tasks. These models are more interpretable because you can take a look at what is retrieved and analyze the correlation with the generation. They are updatable, as I showed you. Like information in the index can be changed. They are adaptable, so we can imagine a setting where a common model is shared to all users, but the precise behavior of the model is controlled by switching the database and make the database specific to a given user. Also, I mentioned that processing document has a cost, but I believe that the trade-off between model size, index size, and the compute allocated to process document is not yet well understood. So I think there is quite a lot of room for improvement in this area. And regarding the problem that these models are strong at, so they are definitively very strong at question answering. And so I think a common theme across the problems that they are strong at is that they usually come from rare topics, or they cover problems from the tail of the topic distribution. And so I think very related to what Zeta Alpha is doing, there is potentially application to scientific domains, which are usually very specific and very specialized. And I imagine this will work well at some point, maybe other domain. And another reason I'm quite excited about this kind of model is that they are very similar to the way humans perform some tasks, as I already mentioned it. So coding and just basically like the decoupling of memorization and reasoning seems relatively natural to me. So that's it for me. Thank you. And we probably have time for a few questions.
All right, thank you very much. Does anyone have a question? Yeah.
Hello, thanks for the nice talk. So I have a question about how to measure the knowledge usage in the generation. And if you see like the knowledge is not used in the generated text, is there any ideas? Are there any ideas to improve this? Thanks.
Short answer is I don't know. And now, so I don't know of any work that like rigorously analyzed how well the knowledge is used for generation. Myself, I've taken a look. In general, for question answering, it's used quite a lot, but measuring hallucination is in general a relatively difficult task. And yeah, so I don't have a good answer to your question. But aside of the fact that the model in general appears to be well conditioned to the retrieve documents. It's half an answer, but I'm sorry.
So this, I have a question as well. This is getting a little bit ahead of ourselves because I think Rodrigo is going to talk about that, but I wanted to give you a chance to comment on it. So what are your thoughts on how to deal with untrustworthy documents, or like, when the documents don't tell the truth, and like dealing with that in a context of like web search and like fake news?
So if you use Wikipedia, it's it solved partially the issue. Like documents are more trustworthy than on the web in general. I assume that on average you will be able to retrieve, like if you retrieve a lot of documents, on average document will be trustworthy. How do you make sure that the model is not exploiting very specific documents to generate something? I have no idea. But so there are some work that are like aimed at filtering like non-trustworthy documents. I think that would be a way to go here. Yeah, it's definitely an issue, but probably also an issue with training of large language models as well.
Thank you. Do you have any other questions, or should we move on to the next talk? 3, 2, yeah.
So thank you for the talk. I was wondering if you see any merit to also explicitly modeling the logical reasoning power of the for the models, like beside just modeling the like a knowledge a word knowledge or like a domain knowledge. Does it make sense to also model like the logical reasoner or something like that to answer the questions or find the answers?
Yeah, I think that like recent work have shown that this is very valuable. Like for the I'm missing the name of the Scratchpad and chain of thoughts work that have shown that it's really useful for language model to condition on some form of chain of reasoning. So I don't see why this could then be integrated to this kind of model. One of the issues that this typically has is that it requires data to kind of prompt this phenomenon. But yeah, I think it's very valuable.